Alright guys, here we go. Let's get rocking on chapter 9, Cellular Respiration, Harvesting Chemical Energy. So I had to steal this picture from the book. I love this panda, he's awesome. So is this a process of turning food into energy? Absolutely. So the focus of this chapter, for each set of reactions that we go through as we talk about this, I want you to focus on, okay, what is this reaction supposed to do? Its location, where is it at? The requirements, what is needed to make it run? And then products, what does it produce? So let's look at our equation for respiration. Our equation shows a glucose molecule, C6H12O6, plus oxygen yields 6 carbon dioxide plus 6 water and energy. Now this should look familiar to you. And here's a really long description of it, a catabolic pathway that releases energy by breaking down organic molecules. And I could keep reading off, but you guys know this. You know that a catabolic pathway, as soon as you hear that, it's when we are taking a complex molecule, we're breaking it down into a smaller molecule, and therefore we're releasing energy. We're getting an exergonic reaction here because this complex molecule here has more potential energy than these simpler molecules on our product side. They have less. So again, it is a reaction that releases the chemical energy stored in organic molecules in our food, and then we use this energy to generate ATP, which is the cell currency of energy. It is the energy currency of the cell, is what our cells prefer. So let's take a look at this reaction. Respiration is a redox reaction. And so what does that mean? Redox is a breakdown of glucose that yields energy as electrons are being transferred from one reactant to another. We're going to get more into this equation in a moment. So what we are seeing happening is glucose is going to yield this energy because electrons are going to be transferred from one reactant to another. So let's talk about what is oxidation versus reduction, because you have to have an understanding of this. How I always remember this was the acronym LEO says GER. LEO is lose electrons, oxidize. GER, gain electrons, reduced. So here's a little table to help you out. When something has been oxidized, so when a compound becomes oxidized, it means that it has lost electrons, it has lost energy, and it has lost hydrogen atoms. If a compound has been reduced, it has gained electrons, gained energy, and it has gained hydrogen atoms. So that's our little table there. Always remember, Leo says GER. So let's take a look at a redox reaction that is similar to cellular respiration in the sense that this is the combustion reaction of methane. And if you have a gas stove at home, this reaction occurs. So we have a gas stove, and you turn it on, and it goes click, 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 and then all of a sudden the flame pops, burns, and then you're going to get your energy. What's happening there? Well, it's the process of methane, this molecule right here, becoming oxidized. What does that mean? Well, CH4 has a lot of potential energy, and we know that because carbon-hydrogen bonds have a lot of potential energy. What it means to become oxidized. Oh, look, it's lost its hydrogen. If it's lost its hydrogen, it also lost electrons. Therefore, it lost energy. Now, this oxygen molecule here has become reduced. Oh, look, it gained hydrogen atoms, and therefore has gained electrons and gained a little bit of energy. So where did this energy come from? Well, it came from the breakup of the CH4. Okay, when that methane became oxidized, that is when energy was released, because we went from a state of high potential energy to a state of lower potential energy, and therefore we get an exothermic reaction. Now, what does this mean? If you want to look at chemistry as to support this, here's why. It will show you the electrons that in between carbon and hydrogen, those electrons are shared pretty equally. But we know that oxygen is highly electronegative. Man, it's got a big pull. And so when oxygen combines with carbon, what do we see? Oh, oxygen's going to pull more on those electrons. And when oxygen combines with hydrogen over here, again, oxygen's going to pull more on those electrons. So what does that mean? Well, these guys are more stable. They don't want to change. Oxygen's got a strong pull, right? They don't want to change. So they have less potential energy than this CH4 because, you know, it was good, but it didn't have a really strong pull. It was more equal and, you know, hanging out. But oxygen, highly electronegative, which means it is a very, very good oxidizer, and we see it in a lot of combustion reactions. Ooh. Okay, so now let's take that and look back at our respiration equation. We have glucose here. Ooh, CHs, high potential energy. Oh, we're going to get a loss of hydrogen atoms. It's been oxidized, lost electrons. Here's my oxygen, high oxidizer, right? It's going to gain hydrogen atoms and therefore be reduced. So what do you need to know? You need to know, Leo says Gur, that when a molecule loses electrons, it is oxidized. When a molecule gains electrons, it has been reduced. And that means gain and loss of energy as well. And we can also look at the movement of hydrogen. But I want you to understand that is where this energy is coming from. Okay? It is by the arrangement of those atoms. Now, cellular respiration utilizes several steps to release energy from organic compounds. So I'm going to flip right back quick. When you learn this reaction, because I know I showed this reaction to my 7th graders, we never talked about what happened from here to here. Well, that's what we're going to talk about. And many of you have already done this in biology or honors biology, but we're going to look at what happens there. You should know that this is not one big kaboom. It's a series of steps. And those series of steps are accomplished by an electron carrier compound. Now, these are molecules that transport or shuttle electrons within the cell. They exist in two forms. It can either be oxidized or it can be reduced. And sometimes you'll see just OX. OX means oxidized. If you see red, it just means reduced. The primary electron carrier in respiration is NAD. Now, NAD is nicotinamide adenine dinucleotide. So we are literally looking at two nucleotides joined together here. And we see that this is a reversible reaction where NAD is the oxidized form. Oh, look, gains a hydrogen though, becomes NADH, and now it has become reduced. And if you want to look at molecularly what happens, we can see the NAD here, where we have adenine attached to two nucleotides. Oh, I'm sorry. Whoops. There's my adenine right there attached. Then, which combines with hydrogen that it gets from food, and then with the use of an enzyme, will become reduced and form NADH. Again, all you need to know is it's an electron carrier, and that oxidized is NAD, reduced is NADH. Now, why is this extremely important? Well, here's why. Because if it's just as similar as if you are driving a car and you have your gas tank is full of gas. Well, it would be very bad if all of that gas was oxidized or combusted at once, because you're going to blow up your gas tank and your car's not going to go very far. Same thing here. That's an uncontrolled reaction. But in our bodies, with cellular respiration, we have a controlled reaction. And this combustion occurs at steps moving down. So that way we can get a release of energy that occurs in a process that, so therefore allowing us to harness that energy and put it to work, making it very, very effective. Okay, so cellular respiration occurs in 3 parts. And there are 3 equations here that you're, not 3 equations, I'm sorry, 3 parts of cellular respiration you're going to have to know. The first one is glycolysis. The second one is citric acid cycle, sometimes referred to as Krebs cycle. And then the electron transport chain is how we'll finish up. So we're going to cover glycolysis really quick because it's pretty short and sweet. Glycolysis literally means splitting glucose. It is a universal step in all types of respiration. Okay, it is that first step of all respiration, and therefore it's likely to be the earliest type of cell energy processes. Its function is to split glucose and produce NADH, ATP, and pyruvate, and its location is within the cytoplasm. So let's take a look at this here. Now, we're in the cytoplasm, right? Cytoplasm, cytosol. We are not even in the mitochondria yet, which is where we know is the energy factory of the cell. So what's going to happen in glycolysis? We're going to break down that glucose molecule into a 3-carbon molecule called pyruvate. And we are going to get a little bit of ATP generated here, where we see some phosphorylation, but we're not going to get a lot. So let's look at the requirements of glycolysis. Short and sweet. You need a glucose molecule. You need 2 ATP, because remember, you have to put in energy in order to break a bond. Okay, so that's the energy that we're going to put in to break that bond. And then we need 4 ADP, and we need 2 electron carriers in the form of NAD. What does it produce? Well, it's going to produce 2 pyruvic acids. These are 2 3-carbon molecules. So we literally took that glucose, split it into half. Okay. We get 2 ADP, 4 ATP, and 2 NADH. Net result, 2 ATP per glucose and 2 NADH. Now, I prefer this diagram. You guys know that I'm a visual person, and when we look at this diagram, this is why I prefer. I put all that stuff on separate slides earlier because I thought, you know what? Maybe you want to go through and be able to separate the what it needs, what it produces, and then the net result. But I really like this diagram. The energy investment phase. Again, we have to put energy in to break that bond. So we're going to see 2 ATP being used to break that glucose. The energy payoff phase. Well, we're going to take 4 ADP and we're going to phosphorylate them to make 4 ATP. And we are going to reduce NAD, which means that we're going to it's going to gain some electrons, gain some hydrogens, and make 2 NADH. And we are left with 2 pyruvate from that glucose molecule. Okay, so what we get here, our net, that glucose yields, makes 2 pyruvate, and we actually get water from it as well. Oops. We get 2 ATP coming from the phosphorylation of ADP, and we get 2 NADHs from the reduction of NAD. Okay, so there is this really big, I showed you guys the other day, really big page of equations in your book that digs us way in depth, and you are more than welcome to look at it and study your little chemist's heart out as much as you want. But as for glycolysis, I'm done. That's it. You just need to know what goes in, what comes out, and then it happens in the cytoplasm. And the purpose of it all is to take that glucose molecule and break it down to pyruvate so that we can head into the next cycle, which is citric acid. See you then.